The title of my talk is the first 3D electron temperature measurements of burning plasmas using novel limited view X-ray emission tomography on the National Ignition Facility. This is joint work with Dr. Benjamin Bachmann at the Lawrence Livermore National Lab. So to begin with, the outline of my talk is to first give an overview on our method, and then I'm going to go on to present our result from both the synthetic and experimental data studies. And then finally, I would like to present you the 3D TE measurement of some recent shot at NIF in the burning plasma regime. The motivation of our work is to produce spatially resolved X-ray emission and electron temperature measurements of the ICF hotspot. In this piece of work, we have applied the iterative algebraic method, algebraic reconstruction technique, to reconstruct 3D X-ray emission distribution of the ICF hotspot and infer its 3D TE. We have also compared 3D X-ray reconstruction with using 2 versus 3 line of sight and make 3D TE measurement using both synthetic and experimental data. More importantly, we have conducted uncertainty analysis on our result, and we believe that our work has demonstrated the feasibility to perform 3D hotspot TE measurement on the NIF. So to give more motivation on our work, 3D hotspot electron temperature can help to further our understanding of the ICF stagnation physics. TE is key to the equation of state together with density and pressure. Also, if we can evaluate TE gradient, then we can study hotspot energy balance and its transport mechanism inside the fusion plasma. So let me now give a quick overview on our method. The X-ray energy that we use here lie between 20 to 30 keV. And in this energy range, the remaining shell of the ICF hotspot will become optically thin. And this can best achieved by the penumbral imaging technique, which has high signal-to-noise ratio combined with high resolution. So as you can see here, the input of our algorithm are a set of reconstructed X-ray penumbral images, 3 of them from 3 different lines of sight. And then the first step is for us to reconstruct a 3D X-ray emission distribution, which is solely geometry related. And then the second step is about inferring the TE from this 3D X-ray reconstructions. So as I already described, the first step is to reconstruct X-ray emission distribution using very few 2D X-ray projection via art. And here in the middle is an analogy, is 2D Sudoku puzzle. So given the projection values in different direction, can we possibly reconstruct the unknown inside the box? And this problem can be transformed to solving AX equal to B, where the matrix A is our projection matrix and the right-hand side factor B consists of the projection values. And generalizing this concept to 3D, we can reconstruct our 3D X-ray emission. And just to give more details on the art, which is a family of regularized iterative method for discretized under constraint inverse problem. So here is the matrix system that I showed in the previous slide. And for more unknown, each row from the sparse linear system actually define an affine hyperplane in a very high dimensional space where the solutions lives, and the solution is exactly living in the intersection of all those hyperplanes. And art is by iterating, bouncing between the hyperplane in the very high dimensional space in order to iterate towards the solution. And the step 2 is about TE measurement, inferring it from the ratio of detected X-ray in different energy channels. So here on the right, we see two 3D X-ray reconstruction in 2 different energy channels. And we can actually plot the X-ray emission ratio as a function of the electron temperature. And by computing the ratio, for example, the X-ray emission ratio for this particular voxel is 1.86, then we can infer the electron temperature to be 4.8 keV. By repeating this process voxel by voxel, we can then obtain a 3D TE map. Now, let me move on to present results from our synthetic data study. The purpose of our synthetic data study is to quantify the systematic errors of our method. Mainly, we want to test the self-consistency and the robustness of our algorithm, and more importantly, to quantify and to study the accuracy of our 3D TE measurement. So here you can see on the left is our ground truth, a synthetic X-ray distribution. And by using two lines of sight, here shown in the middle, one line of sight from the pole, one line of sight from at the equator, we reconstruct a 3D X-ray distribution. And here on the right is the reconstruction by fielding an extra line of sight on the equator. As you can see here, the reconstruction using three line of sight has a more similar shape to the original model than the two line of sight, as shown here in different contour level of our 3D plot. And here, on the left, is just to recap the three model we have just shown in order to quantify the reconstruction quality better. We plot here the XYZ central line out, where the blue solid line is the ground truth, the red one is the reconstruction using three line of sight, and the yellow one is the reconstruction using two line of sight. As we can see, overall, using two and three line of sight, they can capture, we can reconstruct the line out with similar shape, but using a three line of sight, the central line out agree much better to the ground truth than using two line of sight. And when it comes to the TE measurement, here on the left are the three models that we presented in the X-ray scenario. Here on the top is the ground truth 3D TE distribution, and here in the middle is TE measurement using two line of sight, and the bottom using three line of sight. And we introduced another metric called the weighted X-ray TE error to quantify the error in our TE measurement. As you can see here, the absolute TE error is weighted by the corresponding X-ray emission value, and we obtain one scalar number, and this scalar number has the implication that the regions with higher X-ray emission get a higher weight. So with this metric, the lower the weighted absolute TE error is, the better is our TE measurement. And as you can see here, by fielding an extra line of sight, we managed to reduce the weighted absolute TE error by 3 times. So here is a plot of the central line out of our 3D TE measurement as shown in the previous slide. By fielding the third line of sight on the equator, we managed to reduce the relative TE error here to below 10%. As you can see here, while in the Y and Z line out, both two line of sight and three line of sight agree pretty well. Here in the X direction, the extra line of sight further reduced the error. So furthermore, we have tested our method on a collection of synthetic TE model with various shape and geometry, and I'm going to show you 4 in this slide. 4 models, 2 on this slide and another 2 on the next slide. Here you can see that we plot the weighted TE error using 2 line of sight and 3 line of sight, and we also plot their central line out. And again, by fielding an extra line of sight, we managed to reduce our TE error by 3 times in these 2 models, which are ellipsoidal shaped hotspot. And then for these other two models, as you can see here in the central line now, the most challenging model to reconstruct is the torus, is the toroidal shaped hotspot. And by fielding the extra line of sight, we also managed to reduce the error here by 2 to 3 times. So we took a step further here to quantify the statistical errors by simulating the actual experimental noise and adding them to the synthetic X-ray images. Here on the top row are the set of the is a set of synthetic X-ray image, and then we apply the noise additively to this set of image to obtain the images in the bottom row. So we can repeat this procedure 1,000 times and then perform Monte Carlo sampling on the images with random noise. We apply our 3D reconstruction algorithm using two line of sight to this large data set, Monte Carlo sample with random noise to compute the error bars and also probability density function of our TE measurement. So here in the plot, the solid red line is the average TE measurement from the 1,000 random noisy data set. And then the red shaded region is the plus minus 1 standard deviation region of our TE measurement. And in particular, we have chosen 3 voxel here to present the histogram of our TE measurement, which is an approximation to the probability density function. And in this particular case, we observed that the standard deviation ranges from 400 to 600 eV. Now, here is a summary of our error analysis for both the systematic and statistical errors. The 5 models presented here are already shown in the previous slides, and we apply a similar weighted TE error concept to compute a weighted TE standard deviation given by this formula. And here, across all the 5 models, in the systematic error, by fielding an extra line of sight, we reduce the error by 2 to 3 times very consistently across different models. And for the statistical errors, in all these 5 models, we observe that the standard deviation ranges from 400 to 600 eV. And one thing to point out is that the sampling statistic that we use that we obtain here in the statistical errors, they come from a experimental setup that was filled for the past couple of years at NIF, and we recently implemented a new experimental setup where we expect the statistical error bars here to be reduced further by 2 to 3 times. Now, let me transition to the experimental data study result. So we apply the algorithm we have detailedly described to two data set at NIF from the ICEF experiment back in 2019 and 2018. And again, we have 2 line of sight here, a one polar view and one equatorial view. And here on the left is the NIF target chamber, illustrating the geometry and the position of the 2 line of sight. And on the right is a 3D TE map with the input with the X-ray images spatially aligned according to the imaging line of sight. So one challenge that we encounter in processing our experimental data is that because of varying statistical noise on the image plate, the noise can cause discrepancy in the so-called common integrated profile CIP between the polar and equatorial images. So CIP is namely a imaginary line here that I shown with the blue area to which both the polar and the equatorial images are adjacent to. And by plotting the integrated X-ray emission on this imaginary line, in this particular data set, as you can see, there is a noticeable discrepancy in the X-ray on the CIP. And this discrepancy can cause uh, failure of our algorithm to converge because of the inconsistency in our constraint in the sparse linear system. So the question here is how can we match the polar and equatorial CIP without compromising the hotspot structure in the input images? And the solution that we have come up with is to apply the art again, but now in 2D, um, to modify the polar image such that it will match the CIP with the equatorial image. We use the experimental polar image as an initial guess. We put it into a 2D art algorithm matching the CIP of the equatorial image, and we further constrain our algorithm such that the pixel value change has to be smaller than the possible change due to noise. So, as you can see here, before and after the 2D art process, not only does the CIP match now perfectly, but the polar image does not change in any statistical significant way. So now I'm going to move on to present the result from these two data sets. The first one is the shot from 190730. We have the data set presented here. Left column here is one energy channel polar view and also equatorial view. Right column is another energy channel with hotter filtration. We reconstruct a spherical shape hotspot here with the central line out plotted here in both channel having similar shape in the line out. Um, in order to check the consistency of our algorithm, we have uh, done the back projection to the same imaging line of sight to obtain the X-ray 2D X-ray projection image for comparison. So here on the left column are the original input experimental images, and here in the middle column is the back projection image from our 3D X-ray reconstruction, and then we went on to compute the relative error pixel by pixel. And as you can see, the relative errors here in the hotspot are largely zero, indicating that our 3D reconstruction is consistent to the input images. So here we want to again quantify the statistical uncertainty in our 3D TE measurement. What we did is by effectively doubling the noise amount in the original experimental data set. Here in the top row is the original experimental data set, and in the bottom row is the set of images with the additional noise added. The reason why the bottom row images look much more noisier is because the top row images are already blurred due to the intrinsic spatial resolution of our diagnostic. And by using the Monte Carlo sampling uh, on the extra noisy images, we here produce a 3D X-ray measurement, 3D TE measurement with an error bar quantified plus here in the bottom right, the solid red line is the line now of our TE measurement, with the red shaded region being the plus minus 1 standard deviation. And here on the left is a 3D animated hotspot. We benchmark our result with the spatially average TE measurement as shown here. So our 3D TE measurement is consistent with that. And here is the reconstruction result from the other data set that I shown earlier. From the polar view, we see a concentric circle, and from the equatorial view, we saw like a oblate hotspot. So it indicates the images indicate a toroidal shaped hotspot, which we successfully reconstruct here on the top right, and the central line now also confirmed the toroidal shape of the X-ray reconstruction, and we will infer the electron temperature measurement from this X-ray reconstruction. Um, Here again in the bottom right is the central line now of our 3D measurement with the error bar. With the error bar quantifying the providing an upper limit on the statistical uncertainty of our algorithm. The error bar here is larger due to higher statistical noise. And here on the left and in the upper right, we can see we can still recognize some toroidal shape contour in our 3D in the 3D measurement. And again, we benchmark our results here with the spatially average spatially X-ray emission weighted TE measurement, and our 3D TE measurement is consistent. Finally, I would like to present to you the 3D TE measurement result from recent shot in the burning plasma regime. Here is a shot from last year, November. We have two lines of sight, one at the pole and one on the equator, two different energy channel. Uh, the left column is one energy channel. The second energy channel is the right column. We apply the 2D art to match the CIP. The X-ray energy ranges here is from 20 to 30 keV. And we construct we perform the 3D X-ray reconstruction. As you can see here, the distinctive mix feature, the brightest tube feature here, with our algorithm, we successfully reconstruct that brightest X-ray emission feature here as indicated in the central line now as well in both channels. And we went on to produce the 3D TE map with the input X-ray images spatially aligned correctly. Here is the 3D T is the line now of our 3D TE measurement, and again we benchmark our result with the spatially X-ray emission rated average TE. So one very important point here is that we can make use of our result going forward to study, to take a closer look at the difference between between the brightest spot in terms of the X-ray emission and the hottest region in terms of the electron temperature, and the difference between them would give us more information about the mix effect or density effect in the hotspot. So here you can see is our two different view of our 3D TE map presented earlier. On the left, we look at the 3D TE map from the equator, and on the top from the pole, and then I look at simultaneously also the two input X-ray images from the equator and also from the pole, and the brightest feature, the brightest X-ray emission region might or might not align spatially with the hottest region, and again that difference can help us to study in depth about the mixed effect and give us more information in physics. So lastly, here is another shot from last year, October. Again, this shot, as you can see, has very distinctive mixed feature in the X-ray input images. When we do the X-ray reconstruction with the 3D TE map, I can see that the brightest X-ray emission region align with the hottest region here, and here in the bottom right is the line out of our 3D map. Going forward, one other very interesting thing to do is to compute the temperature gradient using the central line out or the 3D TE map that we're shown here. And by computing the TE gradient, it can give us more information about the heat conduction and how it affects the energy balance inside the fusion plasma in the hotspot. And that can give us a lot of insight into the energy balance mechanism of the ICF hotspot. So here we show the summary again. And again, the goal is to have a spatially resolved X-ray emission and TE measurement. With that, I thank you for your attention.